Hi class, this is 1710, acid strength and molecular structure. So strong acids ionize to a greater extent, releasing the protons more readily into solution. Not all hydrogen atoms in the compound are ionizable. Ionizable hydrogen atoms are referred to as Liouville hydrogen atoms. Whether an H atom is ionizable or how easy ionizable it is both related to the structure of the molecule. So basically what this is saying is that strong acids dissociate completely. That means that it releases all of its protons, and that creates the more of a hydronium concentration than what would a weak acid, since weak acids do not release all their protons. When you look at a compound, though, not all H atoms, if it has more than one H atom in it, are ionizable. The ones that are usually tend to be on the end and not in the actual structure, so that makes them easy to leave. And where it is in the structure is basically one of the reasons why as you start looking, you can see a trend of which H atom tends to be the one that's going to leave. Okay, so the more polarized the bond, the more acidic. What that means is polarity, a difference in polarity. So the greater the difference in polarity, the more easily the H can leave, because there's a separation of charge, the more acidic it is. The stronger the HX bond, the weaker the acid. That means that there's not as much polarity. It's going to hold on to that H atom more and more strong. So it's going to hold on, as it holds on to it, it's not going to release it. So that's why it's not going to be a strong acid. Binary acid strength increases to the right across a period. So you can see we have HC, HN, HO, HS, HF. Binary acid strength increases down a column as well. So what does that mean by acid strength and increasing down the column? By looking at this picture, you can see increasing electronegativity is increasing the acidity as it goes this way, and decreasing bond strength increases acidity this way. So we're going to be looking at electronegativity and bond strength. So bond strength and acid strength are inversely related. The stronger the chemical bond that holds onto that H atom, the less likely that bond will break and release that atom. So the stronger the bond, if the bond is not as strong, then then you have a chance of more likely that compound releasing that proton from that compound. The weaker the chemical bond holding onto it is exactly what I said. More likely that bond will break and release the ions. So the stronger the bond, the more likely it's going to hold on to that proton. So if we look here, we have acid strength and bond energy and a type of acid. So you can see with HF, the bond is very strong. And because it's very strong, you have a weak acid because it doesn't want to release that proton. Where you have HCl and HBr, where you don't have as strong of a bond strength, and these are considered strong because these bonds break very easily and these dissociate. So the stronger the chemical bond holding a hydrogen atom, the less likely the bond will break and release the H ions. Now let's look at structural factors. The relative strength of an acid can often be determined based on the structure of the molecule, even without knowing the bond energies. There are two main factors affecting bond strength in a binary acid: the size of the anion and the electronegativity environment around the H atom. So let's take a look at those. An anion size: smaller anions have valence orbitals closer to size of the 1s orbital and have a better overlap. And if they have a better overlap, that means that they have a stronger attraction to each other. So if we compare HF and HI, there's no pictures, but we can read what's happening here. So in HF, the F forms a bond to an H with a 2p orbital and has good overlap between the orbitals. So this has a good overlap. In HI, I forms a bond to HI with a 5p orbital, which is much, much larger. So thereby it doesn't have the good overlap that the HF does with the 2p orbital. So because of that, it's more acidic. It will release that H ion easier than with HF. And HF being a weak acid, it's going to hold on to it because it also has a good overlap. So Ka values can be determined for very strong acids using specialized techniques allowing for comparison. Okay, so if we look here, we have anion size, and you can see this is big and this is small, and ranges and sizes in between. So as the anion in size increases, we can see it goes this way. It also increases in acid strength. That's because of the pore overlap, because these orbitals do not overlap as well. And because they don't overlap as well, think of maybe holding hands with somebody. If you can hold a firm, tight grip, then you can hold on to them easier. But if your hand, you're holding onto somebody's hand and you're having a hard time holding their hand, then that's a weak bonding, and somebody could very easily break apart you guys holding hands. So the overlap really does have a say in how acidic ions compounds are. So a similar trend is seen with group 16 binary hydrogen carbons compounds. We have H2O, H2S, H2SE, and H2TE. So again, if you wanted to take a look at this trend here, we could see decreasing bond strength increases acidity because the overlap is not as strong. Okay, so we go on. Here we go. So now we have bond energy. And we have a bond energy, as you see, increasing bond strength goes this way, and decreasing, increasing acid strength goes in the opposite direction. This makes sense because the stronger the bond, the more likely it's going to hold on to that hydrogen, where in that thereby increases the acid strength. I mean, excuse me, I think I said it's opposite. The stronger the bond, it will not release the hydrogen, and that decreases the acid strength. Where a weaker bond will not hold on to it as easily, as doesn't want to hold on to it as easily, and will release it, increasing the acid strength. Electronegativity. Acid molecules lose ionizable hydrogens. If the bond to the hydrogen atom is highly polar, then the hydrogen atom is already partially positive, making it easier to fully ionize. The more polar the bond between hydrogen and its bond partner, the more easily ionizable the hydrogen be. So if there is, remember, they share electrons. So what is polarity? Polarity is a difference in the partial positive and the partial negative. So if it's easy polarizables, what it means is that there's not a share of electrons, and it's leaving it really electron deficient, partially positive. Because of that, it makes it easier to leave, whereas if it was sharing more equally, there's not as much polarity, and it's not going to give up that bond as easily. That hydrogen as easily. It's going to hold on to it more. So in order for the hydrogen to leave, we want to see a very highly polar bond. Consider the period 2 binary hydrogen compounds. We have NH3, H2O, and HF. We have increasing acid strength as it goes this way, and we have increasing acid strength when it goes this way because of the polarity. But not everything is all factored on this, because if you're looking at HF, it's still a weak acid. So there's got to be other things going on here. So electronegativity increases as you move to the right. So the least polar NH3 is a weak base. Water is amphiprotic, and the most polar is HF, is a weak acid. But in this case, looking at it this way, this is a weak base. Amphiprotic could be an acid and a base, and this is a weak acid. So if we look at it in this terms of comparing these, yes, this is the stronger of the acids, and increasing acid strength going down because of the electronegativity charge. It's not as strong as it is for the fluorine. The more electronegative the Y atom, the stronger the oxo acid. Acidity of oxo acids decreases down a group. So it's the same trend as binary acids. So if you look at the trend here, then you can compare it with the same. It helps weaken the OH bond. The larger the oxidation number on the central atom, the stronger the oxy acid. Acidity of oxy acids increases to the right across a period, opposite trend of binary acids. The more oxygens attached to Y, the stronger the oxy acid. Further weakens and polarizes the OH bond. Okay, so let's take a look at what this is here. The acidity of an oxy acid decreases down a group, helps weaken the OH bond. The larger the oxidation number, so if you remember the reduction in oxidation reduction, you could figure out what the oxidation number is on these, and that would help you determine the stronger of the oxy acid. The more oxygens attached to Y. Remember, Y is the more electronegative atom. So this is, in a sense, this could be the let's say that's an anion. So if it's attached with more oxygens, it weakens and polarizes the OH bond. So if you see here, this one has 3 oxygens and this one has 2. So this one has greater acidity than this one does. A similar trend is seen with acids that contain varying oxygen atoms. More highly electronegative oxygen atoms in the formula generally indicate a stronger acid. So if you're comparing between 2 compounds that look alike and the difference is the oxygens, then this is going to be a strong acid and this is going to be a weak acid based on how many oxygens are there. Similarly, if we look at nitrous acid to nitric acid, this one has more oxygens, so this is a stronger acid compared to this one, which only has 2. All right, so now let's look at structure. So if we look at the structure, we can see that this has 4 oxygens and it's a strong acid, perchloric acid. The H here can easily come off, and a lot of it has to do with stability. If this loses this, it's still very stable because of the double bonds, and you can think of resonance here. It's got a lot that can hold it together even if this leaves. So this is a strong acid. And as you see with this one, we can see with chloric acid, we have 2 that can still handle having this leave. It's still very stable even if the proton leaves. This one is not as much, but still has some stability. And this one, if it leaves, this is going to be pretty unstable compared to the others. So it's going to hold on to this proton as much as possible. Now the electronegativity of Y. So if we look here, we can see that we have HOI, which an electronegativity of Y is 2.5, and it gets a Ka that's pretty weak. But if here, as electronegativity increases, you see that the Ka also increases. So acidity of oxy acids decreases down a group. And you can see that because this Cl in the order on the periodic table, it would be Cl, Br, and I. So you see the Ka actually decreases, even though I wish they had put this in the opposite format to show it. But you can see that this, as electronegativity decreases, then also the Ka also decreases. The higher the electronegativity, the higher the Ka. All right, so now let's look at structure. This has 4 H atoms in acetic acid, but only one of them is ionizable, and that is the one that's off by itself. So when I talk about the hydrogens being by themselves, that's usually an indicator of which one's going to leave. In this case, it's the one attached to the oxygen. Why? Because the oxygen has lone pairs on it, so even if the hydrogen leaves, it is still a stable compound without that. In this case, the hydrogens set in that structure, and to leave them would take a lot of energy. The CH bonds are non-polar, so they're non-ionizable. So they're, if I remember right, hydrogen has electronegativity of 2.1 and carbon's 2.5. So there's only a difference of 0.4. That's non-polar. There is no reason why those hydrogen atoms are going to leave. The H bonded to the highly electronegative oxygen will leave because because of the fact that it's very polar, and making it very polar makes this very partially positive electron deficient, making it very easy to leave, and the oxygens will still be very stable without it. Replacing the non-ionizable H's with electronegative Cl atoms makes the ionizable hydrogen even more ionizable. So basically what this is balancing out the polarity. By changing these, you could change and pull and make these bonds even more polar. And because it's pulling more of the electronegativity in this direction, it will make this even more partially positive, making it easy to pull off. All right, so we can look at acetic acid, chloroacetic acid, dichloroacetic acid, and trichloroacetic acid. So when we look at these, we can see the Ka for acetic acid, where the one hydrogen can come off. And as we start adding chlorines to this compound, we can see that it changes. It makes this even, the hydrogen coming off even easier. It's reduced that number. And if we add 2, it gets even a larger Ka. And if we do 3, it's even a larger Ka. That's because all these are very electronegative, and they're pulling the electronegativity this way. So that's making this actually very electron deficient, and then this one's electronegative. So it's pulling all these polarities in different directions, and in a sense, it's making this easy. It wants to leave it because of all the polarities being pulled in different directions. So rank the following acids from weakest to strongest. So based on these oxo acids, we know that the more oxygens, that make it the strongest. So we select the least polar environment and as the weakest acid, and the most polar environment as the strongest. So you can see, hopefully you understood that this is the direction these go in. How many ionizable hydrogen atoms does each of the following acids have? So if we look at this here, we can see that this looks like it would have 3 on it. This has 2, because we wouldn't touch this one. And this one has 1, 2. We wouldn't touch these because these are actually part of the compound. So if you notice, there's sort of a trend. They're attached to the oxygen because the oxygen has lone pairs on it, and it can balance itself out when the hydrogen leaves, even though the lone pairs are not drawn, and they're usually not drawn, so it's something you would just have to know. But in this case, we can't pull these from this because that would make, those don't want to leave. They really want to stay attached to that compound. So again, 3 ionizable hydrogens on the first one, 2 ionizable hydrogens on the second, and 2 ionizable H on the third, and that's all attached to oxygens, which can handle it leaving. Which of the protons shown in red are more acidic? So if we look at this, we can see that they're very different. We have a carbon with a double bond to an oxygen and an oxygen. So this part is the same, but we have hydrogens here. These are all nonpolar bonds, and that will affect how this compound is, because remember, we want one that has an increased polarity. The increased polarity means that it will make that hydrogen easier to leave. So in this case, there's a difference in polarity here, there's a difference in polarity here. So this is making this compound more polar, which is going to push the H off. It's attached to an oxygen, which can handle this leaving because of the lone pair on it. So in binary hydrogen compounds, acid strength increases with both anion size and electronegativity of the atom bonded to hydrogen. A hydrogen atom is more easily ionized as the polarity of its bond to the rest of the atom molecule increases. The bond to an ionizable hydrogen in an atom is made more polar by increasing the number of highly electronegative atoms near the hydrogen. That's because it's so polar and being pulled in so many directions. I don't want to say it's an unstable, but it's making the environment perfect for that hydrogen to leave. Sometimes unique situations arise that result in an acid being weaker or stronger than would be predicted on bond polarities alone. But bond polarity is usually a reliable indicator. So it's not saying it's a 100% sure thing, but it does give a good approximation of what's happening. In an acid that contains oxygen, all the ionizable atoms, hydrogen atoms, are bonded to oxygen atoms. And all hydrogen atoms that are bonded to oxygen atoms are ionizable. That's because the oxygen atom can handle it. It has a lone pair. It will still stay a stable compound.